All right, let's get a bit into the basal ganglia motor circuits. लेकिन सबसे पहले let's try to get the big picture. The basal ganglia, basically big picture इसकी क्या है? The basal ganglia do not directly cause movement. Instead, they act like a traffic control system for movement. They decide which movement should be allowed, which movement should be suppressed, and how much movement should occur. So anatomy first, the basal ganglia is made of striatum. Now, striatum basically includes your caudate nucleus and your putamen. So this is where you can see this is the caudate nucleus, this is the putamen. They both together make the striatum. Also, the lentiform nucleus includes the putamen and the globus pallidus. When we talk about the globus pallidus, we have two segments of the globus pallidus. The E and I basically stand for the globus pallidus external segment and the globus pallidus internal segment. Then we also have something called as the subthalamic nucleus. This is the subthalamic nucleus in light green on both sides. And below it, you see the substantia nigra. Now, the substantia nigra, you know that because of neuromelanin, which is a little dark in color, it's called the nigra. Now, substantia nigra has two parts to it. This is substantia nigra compacta and this substantia nigra reticulata. So you can see that here. This is the SNC. This is the compacta part. The substantia nigra pars compacta produces dopamine, and the substantia nigra R, the SNR, pars reticulata. Substantia nigra pars reticulata functions similar to the GPI, which is basically the globus pallidus internal segment. We'll see how it functions later on. Um, so basically, you need to understand that the GPI, the global pallidus internal, acts as a handbrake on movement, right? So whenever it's active, the handbrake on movement is active. So whenever GPI is active, there's no movement happening because the handbrake is active, right? Can we understand that? This is like a handbrake in the car. Now, first of all, we look at the direct pathway, which facilitates or stimulates movement, right? So first and foremost, the motor cortex, what happens is, let's look at there are two pathways. There's a black pathway and there's a red pathway. Let's first look at the black pathway. First and foremost, the cortex stimulates. Now, this is the direct pathway. The direct pathway is when you're facilitating movement, right? Now, the cortex stimulates striatum. The motor cortex stimulates striatum, right? When it does this, the striatum releases GABA onto GPI, right? So the GABA is released onto this globus pallidus internus, right? When this happens, the GPI is inhibited. Okay, so GABA is an inhibitory neurotransmitter, and when this is released onto the GPI becomes less active. Now, I told you that the GPI was a handbrake, and since the handbrake becomes less active, movement can happen. The car can move, which means your body can move. Since GPI is less active, it cannot inhibit the thalamus properly. So the thalamus becomes free. This is called disinhibition. You inhibited the inhibitor, right? Since GPI is inhibited, the GPI is off, the handbrake is no longer inhibiting the thalamus, and the thalamus becomes free, the thalamus is activated, the motor cortex is activated, and movement increases. The thalamus stimulates the cortex, and movement increases. Why is it called excitatory? Because the final effect is excitatory. Even though GABA is an inhibitory neurotransmitter, the final effect is more movement. The final outcome matters, and that's why we call this the direct pathway. So the direct pathway summary is basically the striatum inhibiting the GPI, which means less inhibition, and the thalamus and motor cortex becoming free and enabling movement. So the direct pathway, you can remember it does movement, right? So the direct pathway is always creating movement. The other pathway that we need to look at is the indirect pathway. The indirect pathway suppresses movement. This pathway activates the brake, right? Now, how does it activate the brake? The cortex stimulates the striatum, just like we saw in the direct pathway. We're looking at here also. Here also, the cortex stimulates the striatum, but now striatum inhibits GPE. When the striatum inhibits the globus pallidus externa, what happens is the striatum is inhibiting the globus pallidus externa, and striatum is releasing GABA onto the GPE, the globus pallidus externa. Now, normally GPE inhibits the subthalamic nucleus. Can you see here that normally this GPE inhibits the subthalamic nucleus? So when GPE is off, subthalamic nucleus is released. There is no inhibition on the subthalamic nucleus. But now GPE itself is inhibited, right? Since GPE itself is inhibited, the subthalamic nucleus is free, so the subthalamic nucleus becomes active. Now, the subthalamic nucleus, what it does is it basically stimulates the GPI. Again, it's causing disinhibition. I will do this again with you in a bit. So look at this. The globus pallidus externa, basically, what is happening in the other pathway, this indirect pathway, we are overall suppressing the movement because this pathway is activating the brake. The brake is still the GPI, but we're starting with something which was our GPE. Now, cortex is stimulating striatum. Striatum is going and inhibiting GPE, the globus pallidus externa. Now, normally, GPE is normally inhibiting the subthalamic nucleus from doing anything. But since now you have inhibited the GPE, through the striatum, the subthalamic nucleus is free. You have removed the inhibition on the subthalamic nucleus by the GPE. So now GPE itself is inhibited. It can no longer put a brake on the subthalamic nucleus. Subthalamic nucleus is free. It's roaming around again. So now subthalamic nucleus is free. It can do whatever it wants. The subthalamic nucleus stimulates GPI, which we said is the handbrake on movement. So what happens is when GPE is off, the subthalamic nucleus is released, it's free, and the subthalamic nucleus goes and excites the GPI, and now GPI becomes stronger, right? So GPI strongly inhibits the thalamus. And GPI, what happens is when it strongly inhibits the thalamus, the result is less thalamic stimulation of cortex and movement decreases. So GPI strongly inhibits thalamus, right? And less thalamic stimulation reaches cortex. There is decreased cortex activation and decreased movement. So overall, if I look at the summary of this indirect pathway, what is happening is I am activating the striatum is inhibiting the GPE. When I inhibit the GPE, I activate the subthalamic nucleus. There is no more brake on the subthalamic nucleus by the GPE. The subthalamic nucleus is free. And the GP subthalamic nucleus goes and activates the GPI, and this inhibits the thalamus, and less movement is seen. Now, there's an effect of the dopamine here. Now, what is the dopamine's effect? The dopamine is produced by the substantia nigra pars compacta. I'll show it to you here. Look at this. This is the substantia nigra pars compacta. Okay. So this dopamine increases movement by doing two things. There are D1 receptors and there are D2 receptors. Can you see this? Input from substantia nigra compacta. There are D1 receptors and D2 receptors. The D1 receptors are for the direct pathway which stimulate movement, right? So more direct pathway activity means more thalamus activation, more cortex activation, and more movement. This is D1, this is direct. The D2 receptors are basically indirect. Dopamine inhibits indirect pathway neurons. D2 inhibits indirect pathways, and the result is less movement suppression. Therefore, since there is less movement suppression, there is more movement. So D2 inhibits the indirect pathway, right? So why Parkinson disease happens? In Parkinson disease, there is degeneration of substantia nigra compacta, and there's less dopamine. So there is less D1 stimulation and there is less direct pathway happening, right? And D2 is also inhibited, so indirect pathway increases. And the result is too much GPI activity, too much thalamic inhibition, too little cortical activation, and bradykinesia, rigidity, and resting tremor occurs. Okay. So remember also there's a USMLE gold nugget here. Basically, in Huntington disease, what happens is there is early degeneration of indirect pathway neurons in the striatum. Okay, so the indirect pathway neurons here are basically degenerated. Therefore, the indirect pathway is lost, meaning it cannot suppress movement any longer. So you get these hyperkinetic movements, which are also called as chorea. So remember that there are two pathways. The direct pathway removes the brake and it increases movement. The indirect pathway applies the brake and decreases movement. Right? So, dopamine from substantia nigra compacta, D1 stimulates the direct pathway and D2 inhibits the direct pathway. Okay, so in a way, both of them are causing movement. This single concept explains Parkinson, Huntington, and some other diseases, right? So dopamine, since it stimulates the direct pathway and inhibits the indirect pathway, both of the dopamine action in the end through both of the effects is basically increase in movement, right? Um, is there something that I've missed here? You can pause my screen and go over this again. All the parts I explained are here, and I'll stop. This is a very important and confusing concept. I hope I made it easy for you guys.